In this video, we will do some review of parameterization by looking at a practice problem. So the question is from the final practice problems part 2, problem number 3, part B. So I want to parameterize the following curves, and I'm just going to call the curve C, with one set of formulas. So I don't want situations where I have like plus or minus showing up in one of my formulas for X or Y or Z. Okay, so part B is what we're looking at. So I want to parameterize the intersection of these two things. All right, so first what I want you to do is pause the video and try this on your own for 4 minutes. So that might not be enough time to finish the question, but I want to see that, try to begin and see if you can make some progress on this. So 4, 3, 2, 1, pause the video. Pause the video and try this for about 4 minutes. This is, I believe, the most important time in these review videos, the time that you take to actually try these problems on your own, because that's what you're going to be doing during the actual final exam. You're going to be tackling problems on your own, so it's important to practice that skill. And this is an opportunity to do so. Alright, so hopefully you've done that. Hopefully you've paused the video and tried this for about 4 minutes. Let's start to talk about it together. So the first thing to recognize is both of these are planes. So that is a plane, and so is this. So it can help to kind of visualize this particular picture. So I can't always do this in every single parameterization question, but I can do it for the intersection of two planes. And I want to do this because there's actually 2 ways to do this problem. And for one of them, being able to visualize it is the key to the solution. Okay, so if I have a plane, like this, and I'm just going to call this plane 1. And then I have another plane. So another plane, so let's say this one kind of starts up above, and then it comes down, intersects that plane there, comes down, intersects the plane here. Okay, and then here's kind of how they would intersect, and then this blue plane sort of would continue down. That's not great. Let me draw a better line. Continue down. Even the back line would sort of continue down, although it would go below this plane. Sorry, I didn't even label plane 1. Sorry about that. Okay, so this is plane 1. Let me finish drawing plane 2 now. So okay, so I would draw a line here, and then it becomes dashed when it goes underneath. But the intersection is here. The intersection is a line. Okay, so the intersection is a line. And that's useful to know. Intersection is a line. All right, so this other plane I'll call plane 2. So what I need to do is I need to parameterize that line. And we've actually done an example of this before. One of the ways that we can do this is I could take a normal vector to one of the planes. So let's say I take a normal vector to plane 1. Normal vector to plane 1. And I call this N1. So N1 is normal to plane 1. Okay, now let me draw a normal vector to plane 2. So this one's going to be sort of angled. So angled like this. This one's calling this N2. And that's normal to plane 2. So if we take those two normal vectors, and then I form their cross product, so if I use the right-hand rule, and I take N1 cross N2, it's going to point in a direction that's perpendicular to both of these planes. And that will be along this line right here. Sorry, I think I said perpendicular to both of the planes. That was wrong. I meant to say perpendicular to both of the normal vectors. Right, so that is going to point in the direction of the line. Okay, so this is N1 cross N2. All right, so I got the picture. Let's try to solve for this. And I'm going to do this in 2 ways. Okay, so for the first method, I'll call method 1. And that's going to be to use this picture and to use these normal vectors. use the picture and use the normal vectors. Okay. So the first thing that I need to do if I'm trying to parameterize a line is I need to get a direction vector in the direction of that line. Okay, so the direction vector we know based off of the picture, direction vector, at least we know how to find it. We need to take the cross product of n1 with n2, where n1 and n2 are the normal vectors. So looking at my plane equations, the normal vector to a plane equation, once I have the constant on its own on one side, the normal vector I get by taking the coefficients. So the coefficients here are, there's technically a 1 in front of the x, 2 in front of the y, 3 in front of the z, and those coefficients make up my normal vector. So 1, 2, 3 for n1, and then cross that with n2. For n2, I'm going to have to take the 2z and move it over, and then I can do the same thing, and I'll get 4, -1, -2. All right, so let's take that cross product. So we will get determinant with I, j, and k at the top. And then I write the first vector, 1, 2, 3. Then the second one, 4, -1, -2. Okay, so doing the determinant, we will get I times the determinant of 2, 3, -1, -2. So remember, the way that I got that sort of smaller determinant was I cross out the row I is part of, and I cross out the column it's part of, and then I write down the determinant of what's left over. Okay, let me undo that. Okay, so now for the next term, I put a minus sign, and I go to j. I do the same thing, and that'll leave me with 1, 3, 4, -2. And then I go to k, and I switch back to positive, so plus k times the determinant of 1, 2, 4, -1. All right, so if we evaluate this, for the I determinant, I'll get -4, and then plus 3, I hat. And then I have minus, for the j one, I'll have -2, -12, j hat. For the k one, we'll have -1, -8, k hat. All right, so we got negative I hat plus 14 j hat minus 9 k hat. Okay, so this is a direction vector. It's a vector in the direction of that line. Now what I need to get still is I need to get a point on that line. Could be any point. Okay, so how can I get a point on this line? It's a point on this intersection line. So we're trying to find the intersection of these two planes. So let me just write down their equations, just so we have them here to work with it. So we get x plus 2y plus 3z equals 12. That was one of the equations. And the other one was 4x minus y minus 2z equals 8. So I move the 2z over to the left. Okay, so I know based off the picture that there should be an infinite number of solutions to this system of equation, because there's an infinite number of points that are on the line. And I have these two equations, but 3 variables. And that means that one variable is free, which means I could pick any value that I want for it. Okay, so one variable is free, so I'm just going to let z be equal to 0. I'll pick a simple value, and now I'll plug that into this into my equations. So the first equation becomes x plus 2i equals 12. The second one becomes 4x minus y, just that, and then equals 8. All right. Whoops. Sorry about this. Sorry about that. Okay, so, all right, so what I can do is I'm going to multiply the second equation by 2. So keep the first equation how it is, multiply the next one by 2, and I'll get 8x minus 2y equals 16. And I'm doing that so that now I can add them together and cancel the two y's. This is one way to deal with a system like this. Another way would be to isolate one of the variables and to substitute into the other equation. Okay, so if I add my equations now, let's add these. We end up getting 9x equals 28. So x equals 28 over 9. And from here, this part's just algebra. If I were to plug this back in to figure out what y is, I would end up doing some work. A little bit of arithmetic, and we end up getting 40 over 9. So I'm skipping some of those details there because they're not too bad, and I'll leave that for you to work out. Okay, so at this point we have a point on the plane. X is 28 over 9, y is 40 over 9, and z, well, we started this part off by saying let z be 0. And we have that flexibility because there should be an infinite number of points on this line. So if I had wanted to make z equal 1 or z equals negative 100, I could have. Okay, and then the direction vector, we had direction vector. We also solve for that. Direction vector is negative 1, 14, negative 9. All right, so once I have my point and once I have my direction vector, we are ready to write down our parameterization. So I'll just write P-A-R''N for parameterization to abbreviate. Okay, so x of t is going to be the x coordinate of the point, 28 over 9. And then I take this coefficient of the direction vector, minus 1, and multiply it by t. So we get 28 over 9 minus t if we do that. Same thing for the y's. So y of t is going to be equal to 40 over 9 minus 14t. Same for the z's. Z is going to be equal to 0 minus 9t. So I'll just write minus 9t. Okay, and because we're talking about the whole line here, this infinite line, I need t to be any real number. And that's my parameterization. Okay, so I want to do this in one other way. Okay, so I'm going to call this next method just method 2. So it's helpful sometimes to see multiple ways to do a problem in one reason, because that's often the case, that problems can be solved in a multitude of ways. But the second reason why is, for a timed test like the final exam, it's helpful to know the different approaches to do a question so that we can pick the most efficient one and save time. Okay, so in method 2, what I'm going to do is I'm going to let one variable be t, and then sort of follow that to figure out what the other variables would be. Okay, so the equations, again, I'll copy them down. For x plus 2y plus 3z equals 12, and 4x minus y minus 2z equals 8. Let's write that 12 a little better. So 12, I'll call this equation 1, this one equation 2. Okay, so I'm going to let one variable be t. Doesn't really matter which one here, so I'll just let z be equal to t. So then equation 1 becomes x plus 2y plus 3t equals 12. And equation 2 becomes 4x minus y minus 2t equals 8. All right, so we have these two equations. I want to now know what x and y are. So let's solve for x or y in one equation, and then substitute into the other, and substitute into the other. Okay, so I'm allowed to do stuff like take one equation, isolate for a variable, and substitute into the other one, because we're talking about finding the intersection of these two planes. Okay, so for example, in equation 1, if I isolate x, we'd get x equals 12 minus 2y minus 3t. So let's take that and let's substitute that into equation 2. So instead of having 4x, I would write 4 times, and now I'm going to plug this in. So let's plug in 12 minus 2y minus 3t. And then we have that minus y term, and then minus 2t. Okay, and this whole thing equals 8. So if I simplify this, I could distribute the 4 and get 48 minus 8y minus 12t. Okay, the other terms I'll copy down again, so minus y minus 2t equals 8. So we could combine some like terms. Negative 8y minus y, that becomes negative 9y. And then negative 12t minus 2t is negative 14t. But let's start to move that to the other side. So that'll become positive 14t. And if I also move the 48 over to the right-hand side, 8 minus 48, that's negative 40. All right, and then we divide by negative 9, and we get y equals negative 14 over 9t plus 40 over 9. Okay, so finally we have y as a function of t. That's the type of thing that we'd need for the parameterization. Okay, so now we could take this. We could take this and substitute this back into our equation for x. Okay, so we end up getting x equals 12 minus 2 times y. So 2 times y is negative 14 over, negative 14 over 9t plus 40 over 9. And then on the outside, sorry, I still have that minus 3t. Okay, so with this, we just do a little bit of arithmetic, and we could simplify it. So we do a few steps, which I'm going to skip because they're not too bad. I want to get more to the heart of the problem. X, if we simplify this, get 1 over 9t plus 28 over 9. Okay, at this point, we now also have x written as a function of t. So we are ready to write down our parameterization. So x of t equals 1 over 9t plus 28 over 9. Y of t was equal to negative 14 over 9t plus 40 over 9. And then z of t, remember we started this whole thing off in method 2 by letting z of t just be t. We let z be equal to t. All right, and because we're parameterizing this whole line, we need t to take on all real values. So t can be any real number here. And that's my parameterization, doing it the second way. So if we compare this to the answer that we got from method 1, let me flip back. They look a little bit different. So I do see the 28 over 9, I do see the 40 over 9, and then no extra sort of term with a negative 9t for z. And I see those numbers here as well. I see 28 over 9, 40 over 9, and then kind of like nothing. So that's good, because if I were to plug in t equals 0 into either parameterization here, we actually show that they go through the same point. They go through the point 28 over 9, comma 40 over 9, comma 0, if you plug in t equals 0. So that's the case in either parameterization, either this one or the one on the previous page. But then we might say, oh wait, the coefficients of t look different. What's happening there is, if you were to use this direction vector that we did in the first parameterization, if you were to form the direction vector from parameterization 2, it ends up being a scalar multiple of the direction vector from parameterization 1, and that's fine, because it's just scaling that vector, but that doesn't change what line we're talking about. All right, so that is it for this example. In the next video, we are going to do some review of the dot product and its application to work.